Hello, I'm Bonnie Meinke, and I am an astronomer at the Space Telescope Science Institute. And we're here today to talk about eclipses as they relate to astrophysics. When we think about eclipses, we normally don't think about astrophysics. We think about our solar system. We think about the geometry that sets up an eclipse when the moon moves between the Earth and the sun. We have been able to use eclipses because they're naturally occurring. Solar eclipses have allowed scientists throughout human history to be able to probe what's behind the sun due to the actual physical disk of the sun being blocked. So all of that light is dimmed. And through that, we've learned a lot about not only our sun and our solar system, but about other stars and about the laws of physics. Light does not travel in a straight line on space-time. In fact, when a massive object bends space-time, it bends the path that light would take around that massive object. General relativity is the idea that space-time is warped. Space-time curves like a fabric of the universe, and it curves around massive objects. These are things like planets, stars, galaxies, even black holes. In our own solar system, the most massive object is our sun. So the best way to test ideas of general relativity would be using our sun. We have the opportunity to observe this bending of light using a solar eclipse. When a star, or our sun in this case, is blocked during an eclipse, you're dimming it by a factor of 1,000,000. When we dim it by over a factor of 1,000,000, you can actually see stars on the other side of the sun. Arthur Eddington figured this out, and he wanted to test it back in 1919. So he went to an island off the coast of West Africa, and he sent another team to Brazil. They both took observation of the Hyades star cluster before the eclipse commenced and then during the eclipse. And they saw a change in the position of the cluster in the sky of about 1/2000th of a degree. That's the same as a right triangle that's 1 inch on one side and 1.9 miles on the other. It's a very small angle, but they were able to measure it in both locations since they had good weather and confirm that this idea of the bending of light due to general relativity was true. So this is one of those great examples of eclipses being used in astrophysics and physics in general to understand how our universe and the laws of physics work. One of the other great uses of eclipses is as a detection method for exoplanets. So what we look at are transits, which aren't true eclipses because the disk of the planet never fully obscures the disk of the star. But if we get the right viewing geometry and the solar system that we're looking at is edge on to our line of sight, the planets will pass in front of the star and we will see a dip in the light of that star. So we'll see a slight dimming, and that slight dimming tells us how big that planet is. This is a great way to discover exoplanets. And we've done this from the ground, we've done it from space, including using missions like the Kepler mission. We've discovered thousands of exoplanets using the transit detection method so far. But I will say that this is an indirect method, which means that we're inferring that an exoplanet exists around that star. So eclipses have been incredibly useful for studying our own sun in our own solar system. But what about other stars? Well, we don't have the right geometry to be able to perfectly block the disk of another star using natural methods. So we have to create an on-demand eclipse. And this method is called choreography. You use an instrument called a coronagraph to perfectly block the disk of that other star. And in doing so, you dim the light around it, and you can see the fainter objects that are nearby. We are directly imaging exoplanets using this method. And this is wonderful because we get to study a whole new field with this called comparative planetology. We get to look at what those exoplanets are truly like, the various characteristics of them, size, atmospheres, things like that, and compare those to our own solar system and the planets therein. That way we get to see, is our solar system an oddball or is it the norm? Choreography is so useful that it's been used already in many ground-based observatories and space-based observatories such as the Hubble Space Telescope. One example of this is the Fomalhaut B system. You can see this planet, maybe a brown dwarf, orbiting far away from the blocked star. And we've been able to observe this using choreography multiple times over many years. We plan to use this method on future observatories, both ground-based and space-based. The space-based observatories we plan to use it on include the James Webb Space Telescope and WFIRST. And as we look at more and more exoplanets using choreography, we'll learn more and more about our own solar system as we compare it to others.
Well, we hope that you really enjoyed that special edition of our Eclipse webcast. As always, you can get in touch with us by posting comments below on the YouTube page. You can get us on Twitter at @NatSolarObs or on Facebook at www.facebook.com/National Solar Observatory. Or you can follow us on Instagram. Our handle is @National Solar Observatory. We'd love to hear any questions or comments you might have about the webcast, anything else that you'd like us to cover in the run-up to the solar eclipse, and we hope to see you again next month.